Hello, I am Anastasia Pustozerova, and I'm a machine learning researcher at SBA Research. It's a IT security company, and I'm also a PhD student at TU Vienna, the Technical University of Vienna. And today I will give a talk about federated learning, the current status of federated learning, and which challenges exist now in this area. So let's start. As we all know, machine learning is used in various industries nowadays, and it demands quite a big amount of data to build models with high effectiveness and good predictions. However, data used for machine learning often contains private or sensitive information. And the leaks of this information can cause problems for companies when competitive information can be sold and used by competitors, and also for people whose personal, financial, and health information can be sold or used for marketing or fraud or other bad things. So in April 2016, European Parliament has enforced General Data Protection Regulation, or GDPR, and many companies have faced issues of implementing privacy-preserving machine learning tools. And privacy-preserving machine learning can be split into two categories. The first one is privacy-preserving data publishing, is when you can publish your data set, but you anonymize it first with techniques like k-anonymity, L-diversity, or T-closeness, or use differential privacy in a way that none of the instances of the dataset can be identifiable. And then you can use machine learning algorithms for processing this data. However, these techniques can cause also the loss in effectiveness. So you have always this need to find the threshold between privacy of the data and effectiveness of the model. The other approach is privacy-preserving computation. It includes this kind of techniques like homomorphic encryption. It's the technique when you encrypt your data before sending it for the following processing. Then the server or the other party processes the data there and sends you back the results, which you can decrypt only locally. However, this approach is computationally costly, and it supports very limited number of operations, only multiplication and sum. Industries are not tend to use it much because it's very computationally costly, as well as secure multi-computation. It basically allows to several parties to compute jointly secure the function over their inputs. However, this approach is also very computationally costly, and therefore federated learning comes as a very interesting alternative on how to preserve privacy-preserving machine learning. So what is federated learning? Imagine we have several medical institutions who want to train the model predicting, let's say, lung cancer. However, due to various legal and bureaucratical issues, they are not able or not willing to share their patients' data. In this case, federated learning allows us to train machine learning models locally at each institution on their local data. And then each of these institutions, after training the model on the local data, sends this model to the federated server. So unlike in classical centralized learning, when we aggregate all the data in the server for the following processing, here we aggregate only models. Federated server then averages these models to get the global model, and then it sends this global model back to the hospitals for the following processing, or already for the usage locally inside the hospitals. Therefore, federated learning addresses the problem of data locality and ownership. So we don't need to transfer this sensitive and private data, and we can train machine learning models closer to the place where data originates. Federated learning can be applied for different tasks, not only for medical domain, where it's actually very actual, but also for Internet of Things and mobile computing. Federated learning also can be considered with different number of processing nodes, again, starting from several medical institutions to billion of mobile devices. Also, federated learning can be used with different machine learning algorithms like regression, neural networks, or decision trees. And it can have different communication architecture. So here we'll introduce several types of federated learning architecture. So on the left, you can see centralized or client-server architecture, which is basically described in the previous example with hospitals. The model of the process of federated learning starts with random initialization of the model, which is then sent to each local node. Afterwards, each local node trains this model on its local data and sends it to the server, which aggregates model afterwards. The other type of architecture of federated learning is decentralized or peer-to-peer architecture. It can represent, for instance, sequential learning. When we initialize some model at one node, then it trains it's on its local data, sends to the next node in the sequence. This one sends to the next node in the sequence, train on this local data, and then this process can also repeat in several cycles. Also, the other type of learning can be the decentralized peer-to-peer architecture, architecture when each node trains model locally and sends model to other nodes, and already inside itself, node aggregates the models from each other participants of the training. Therefore, we don't need to have any centralized server or aggregator in the setting, and the learning comes only with peer-to-peer. So the advantages of federated learning is, of course, that it avoids sharing of sensitive data and we share models instead. Also, it allows all participants to gain some benefits from all the data. And it allows us to distribute a computational load to the clients from the server. However, there are still a lot of challenges in federated learning, and one of the biggest ones is communication costs, especially when you have the large number of nodes in the setting. The training process might be time costly. Also, the problem is unbalanced data when different nodes has different data of different distribution or different classes. In this case, the number of federated cycles may be higher, and it might take more time for the model to converge. The other problem is system heterogeneity. Systems heterogeneity is probably more actual for the IoT domain. When you have 4 different devices, there is different volume capacities or different battery capacities, and it also might influence learning process. And also there is still some security and privacy risks. And in my research, I'm actually focusing on security and privacy of federated learning. Currently, I'm working on the project Feature Cloud. The project is financed by European Union in the frame of the program Horizon 2020. And the goal of the project is to build a platform which will allow do the research and process sensitive medical data without violating privacy of the patients of different hospitals. My task on this project is to evaluate privacy and security risks of federated learning, which is used as a base mechanism in the project of secure machine learning, secure and private machine learning. So I'm working with federated learning, effectiveness evaluation, also compared to centralized learning. I'm evaluating privacy and security risks in federated learning, and also considering the mitigation strategies, which can be used to reduce privacy and security risks in federated learning. So as I already told, in federated learning, we share only models. We don't share the data. However, the problem that models can still leak the information about the data they were trained on. There exists a number of attacks which are targeted to infer some sensitive information from the model. These attacks are represented here. One of them is model inversion attack. You can see the results of this attack down here in this picture. Basically, the authors of the paper who presented an attack, they trained the machine learning model on the data set, which is called 10 personalities. The machine learning model was predicting who is depicted on the picture. And the authors of the paper were able to reproduce and to recreate the picture of the people just having access to the model. And as you can see, the picture looks quite similar to the original and might be a very dangerous attack. The other type of attack is RGB disclosure. RGB disclosure attack considers the scenarios when an adversary has some part of information about the instance. For instance, he knows the person's name and address, and using the model, he wants to infer the date of birth of the person. And the other type of attacks, which is my research was the last year focused on, is membership inference attack. It's basically when an adversary wants to find out if some data record was in the training set of a model or not. This attack seems to be very powerful and give very high performance even with black box access to the model when you don't know the parameters of the model and you can only query it. But even in this scenarios, attack may give like 90% of accuracy if some instance was in the training set or not. And I was performing the experiments of membership inference attack in federated learning settings. And of course, federated learning was also vulnerable to this type of inference attack. Therefore, there is still some mitigation strategies are needed to improve the privacy properties of federated learning. This kind of mitigation strategies can be considered, and they were already described in a couple of papers. The first one is secure multi-party computation, which you can impose on model parameters before sending to the centralized server. You can do secure multi-party computation on models to average them. The other approach to mitigate the privacy risk and differential privacy is to basically perform differential private machine learning and then to aggregate model parameters. And the other approach that can be used is homomorphic encryption, when we can send we can encrypt model parameters before sending it to the server, and then on the way back we decrypt them. These approaches are still considered and currently considered, and they might bring some additional communication costs. So really here you need to find a threshold between privacy properties of federated learning and effectiveness and efficiency of the approach. So the key points here is that federated learning is actually cool, and it allows us to perform machine learning on distributed data without sharing sensitive information. And the approach is not so computationally costly as secure multi-party computation homomorphic encryption. And it also allows us to distribute computational load to the client, so we can train several models in parallel instead of train everything on the server, which might even be more time consuming. However, federated learning still has a number of open issues, including like data and system heterogeneity, communication costs, which can influence the effectiveness and efficiency of the process. And also federated learning does not guarantee full privacy by the default, and it also requires some additional mitigation strategies to reduce privacy and security risk in the setting. Yeah, that's all. Thank you for your attention. I will gladly now answer any of your questions.